Hi, I'm Anil Kang. I'll be presenting our ICLR work on efficient edge inference by selective query. Our problem setup consists of edge devices, namely microcontrollers or mobile phones. Following an image classification problem, based on the hardware, you can only deploy tiny models such as MobileNet V3 or MCUnits on this device. Typical deployment constraints in such setting includes model size, compute usage, battery drain, and inference latency. For illustration, we'll use a typical microcontroller with 320 kilobyte SRAM and 1 MB flash storage, and we'll solve ImageNet classification task. The first baseline that one can deploy in this setup is an on-device model. Basically, pick up the best performing model under the constraints using a combination of techniques such as compression, quantization, distillation, or architecture search. MCUNet has a family of models that you can deploy on this device. It achieves an accuracy in the range of 50 to 62% accuracy, which is low on this task. Here we show inference latency on the x-axis and energy on the top axis. Although the accuracy is low, the on-device models have low inference latency and consume less energy. Another solution is an on-cloud method. Here the edge model simply sends all the inputs to the cloud and incur a communication cost in the inference latency. Simplicity will assume the cloud model to achieve 80% accuracy. Clearly, as you can see, the accuracy is much higher than the on-device methods, but it has much higher inference latency and it consumes significantly higher energy. To leverage the cloud model effectively, let's see if we can route only few queries to the cloud. Basically, for an easy example, such as a panda image in this case, the tiny model on the edge device can handle the inference locally, resulting in low inference latency and energy consumption. In contrast, for a hard example such as a bear image in this case, the model being uncertain in its predictions routes the examples to the cloud and takes a hit in the inference latency incurred in the communication. The main idea is to leverage the edge model or the cloud model based on the input hardness. Let's formally define a hybrid model. Consider a hardware setup with compute devices on the edge and the cloud. We'll deploy a tiny low capacity model on the edge named base and deploy a high capacity model on the cloud named global. We'll place a router on the edge. This measures the confidence on the base model prediction. It keeps the easy examples on the base and routes the hard examples to the cloud. We can define coverage as the fraction of examples kept on the base model. Similarly, we can define hybrid accuracy as the accuracy of examples at the base plus the accuracy examples on the global model. Finally, we can write the optimization as maximizing accuracy subject to the coverage constraint. Given any pre-trained base and global models, we can learn the router using the following objective. Note that without any coverage constraint, the ideal routing looks like this function R that sends the inputs to the global model only when the base is incorrect and the global is correct. This gives us the oracle O. Hence, we can learn the router using a binary classification using the oracle supervision under the coverage constraint, where the coverage can be relaxed using the following loss function. Given the feature space, we will run the router on this resulting in the decision boundary, separating data points for the base model. The base model will learn a weighted variant of the classification loss to favor this region. Similarly, the router assigns hard examples to the global model, where the global model learns a weighted classification loss to favor this global region. Finally, we learn these three models in an alternating fashion, first learning the router, then learning the global model, and then learning the base model. In contrast to the dynamic and other adaptive baselines, hybrid models closely match the upper bound on the latency accuracy trade-off. It achieves the cloud model accuracy with nearly 25% reduction in inference latency. So far, we have used edge cloud setup where the base and the global model live on different hardware. We can also deploy hybrid models on the same device. In doing so, we can adaptively generate all the intermediate budget models from the smallest and the largest in the family. In addition, we can achieve up to 3% increase in accuracy and up to 1.5x reduction in max. Finally, after training the hybrid models, we can operate without the cloud model, leading to an abstaining classifier that predicts on easy examples and rejects hard examples. To summarize, hybrid model selectively sends hard inputs to the cloud. They learn router via proxy oracle supervision. They are deployable in edge cloud setup as well as on the same device, and they act as an abstaining classifier without the cloud model. Thank you for listening to the talk. Please visit our poster for more details and check out our implementation at the following GitHub repository.